Dear friends, Maths Aspirants is a community of mathematics students, research scholars, and faculty members across India, initiated by myself in 2017. And we used to organize several programs to help the students in the field of higher mathematics, especially in their preparations for different national level competitive examinations like IIT, JAM, CSIR, NET, GATE, NBHM, etc. We used to organize online problem solving sessions, especially by research scholars and postdoctoral fellows and young faculty members. So I'm sure that such sessions will be really very motivation for you to crack these exams. Today, I am very proud to say that we have one of the best resource person with us, Mr. Samit Ghosh. He is currently pursuing PhD at IISER Kolkata. He has did his M.Sc from Baligan Science College, University of Calcutta, and he qualified CSIR NET with JRF and GATE examinations, and also last year he is awarded the prestigious NBHM Doctoral Fellowship. And with that fellowship, he is currently pursuing PhD in the field of geometry and topology at IISER Kolkata. So I'm sure that his session on basics of linear algebra will be an eye-opener to all of you. Will help you to crack more problems in an easy manner. And all of you know that linear algebra is one of the important topic in any competitive examinations. There will be a lot of problems from this particular area. And also the fact is that comparatively, since from linear algebra are easier as compared with analysis portion. If you have that a strong concepts and have a practice of doing problems, certainly you can crack maximum mark from this area. So I'm sure that Samit will certainly help you through this today's session to get a good mark from linear algebra part. So I welcome everyone to this program, and I would like to express my sincere gratitude and thanks to Mr. Samit for accepting our invitation and joining with us in his busy schedule of PhD coursework and all that. So welcome everyone to this program. Welcome, Samit.
Okay, so good morning to everyone, and first of all, so thanks to Professor Vinod for inviting me, and I'm great pleasure to share my knowledge about mathematics and passion about mathematics in such an audience, in front such an audience, and thank you for the opportunity to contribute from me for Maths Aspirants group. Okay, so basically today we'll talk about the good problems on linear algebra. And linear algebra is very important topic. Is not only particular is a competitive exam. So this is a very basic topic, and this will lie in every field in mathematics. So it will play an important role when you study the differential geometry, when you study that topology, algebraic topology, general topology, anything. So and Lie group, Lie algebra. So this will very important play, and also so good problem is not particularly important for exam purpose. So this will actually encourage to you in mathematics also, and and also you build a problem solving skill as well. So today basically so we are focusing on one set of problems, and this set of problems is basically lie on various important concepts from linear algebra. So So today we will talk about mostly four set of four problems. So one problem is based on basic concepts on vector spaces and the linear covering of vector spaces. Okay, and another problem is very interesting problem. So, and that problem we will tackle using the tool of linear algebra. And basically these problems indicates that, and basically in this problem we will characterize all polynomials over R whose image under integer is again an integer. It's a very interesting, and we will totally tackle this problem using the linear algebraic tool. And another problem is it is also very important topic for competitive exam is a rank on matrix or rank of linear operator. And so these problems is based on that concepts. And here we will give you a application of the Sylvester's inequality. Okay, so it's a very interesting and powerful inequality, and that will help you a lots of to solve the lots of problem. And another is a very classical theorem, is a Cayley-Hamilton theorem. And now we will focus on the Cayley-Hamilton theorem for 2 dimension. Okay, so also it is true for any n dimension case, but here we will talk about only 2 dimension because of, so okay, so there is a is very related to the computation of power of matrix 2 cos 2 matrix. And yeah, so in this problem we will talk about, and we will talk about some application of the Cayley-Hamilton theorem. And now I will give you an algorithm for computation of power of 2 cos 2 matrix is any power of 2. Okay, if you choose any 2 cos 2 matrix, you will always compute the power of 2 cos 2 matrix using the Cayley-Hamilton theorem and the binomial law. It's very, very interesting. And okay, so okay, so okay, and also, and that algorithm is okay, so particularly in this problem 4, the problem 2a and b, so this is particularly based on the power of 2 cos 2 matrix. Okay, so the power of the computation of power of a matrix is not important in the theoretical purpose only. So this is very, very important play in the data science as well as computer science and cryptography, cryptology is anywhere. So that's why that we need to take care the computation and algorithm. Okay, so to compute the power of a matrix. Okay, okay, and also during the problem solving session, if you have any questions and if you have any doubts, so you can easily freely ask me. Okay, and raise hand. Okay, so don't hesitate. Okay, so also I am so related to problem 1. I will give you some interesting result about that, and this result is basically by Professor 𝕄𝕒𝕚𝕚𝕚𝕚, and now he is recently he has got the Shanti Swarup Bhandagar Prize, and this is the most highest prestigious scientific award in the India. Okay, so and also I hope so all of you enjoy during this problem session, and I'm request to all of that please involve with me and try to okay, so contribute. Okay, and basically I'm one to these problem session is very interactive, not from one side, not from only from my side, also I am expect from anything from other side. Okay, okay, so so first problem. Okay, am I audible? Hello?
Yes.
Yes, sir.
Okay, so first problem is all of you know that R plus, okay, so is a set of all positive real number. And so can you make a vector space structure on R plus over R? Is there any techniques? Usually R plus is not forms a group. Okay, so under addition, usual addition, right? So how can you define the addition on R plus and suitable scalar multiplication so such that that forms a vector space over R? So is there any idea? So if you have anyone, so then please share me. Any idea? Okay, so how can we approach this problem? Okay, so first of all, is there any bijection? Is a standard bijection from R plus to R? Is there any bijection? Anyone?
If you're going to consider from R to R plus, you have e power x.
Yeah, so, and what is the inverse of that function?
The log function.
Good. So we have a standard function from R to R plus. So fx is equals to e to the power x, right? And what is the inverse function? The inverse function is g from R plus to R. And so gx is equals to ln x, right? So now, so this is bijective. Why it is bijective? The ln x function is why it is bijective? Okay, so one, you can think about the graph of the ln x, right? So this is the positive, this is actually R plus section from that to that, and this is 1, okay? And the graph of ln x is something like that, right? So this is 1, okay? And clearly, so it is injective and it is surjective on R, right? So if you choose any point, so it is cut exactly one time of the graph of ln x, right? So therefore it is bijective map. Or also you can prove the bijectivity using some analytical concept, because ln x is a strictly model function, right? Okay, so therefore it is injective, and also surjectivity you can follows from that graph. So it is bijective map. So now the question is that, and it is very standard phenomenon in the particularly mathematical structure. Okay, so suppose X is any set and Y is a mathematical structure. So this structure may be vector space, maybe field, maybe group, maybe ring, anything, any mathematical structure, Lie group, list, Lie algebra, anything. Okay, and if you have a bijection from X to Y, and suppose Y is a topological space, okay, and Y can be also a topological space, right? So if you have some bijection from X to Y and Y have some special structure, so using that bijection, you can pull back that structure on capital X. Okay, and basically that structure is basically the isomorphic structure. You can pull back the same isomorphic structure from Y to capital X, right? So already you know that capital R is a vector space over R, right? Okay, so we know capital R is a vector space over R. Okay, so now we pull back that vector space structure on R plus. So how can you define the addition? Is anyone using that bijection? So we define xy belongs to R plus. We define the addition that x plus y is equals to what? X plus y is equals to G inverse of what? G inverse of gx plus gy. Clear? So G inverse of gx plus gy. So gx plus gy is a member of R. right? And take the inverse image. So this is a member of R plus, right? And you can define the scalar multiplication, and Y is, so let C belongs to R and X belongs to R plus. So then Cx is equals to, you can define that, okay, so G inverse C Gx. Okay, so under addition or under this scalar multiplication, you can check it. So this is a vector space over R. Okay, so exercise. Okay, so check it. So suppose, so this is not our usual addition. So this is that, and the scalar multiplication is that. So that, okay, so R plus, okay, so this is a vector space over R. Vector space over. Okay, and now what is the dimension? So is this vector space over R, is this vector space R plus over R, so it is isomorphic to, it is linear isomorphic to R. So note that, so actually this bijective map G, so this will produce, basically give you the linear isomorphism, right? So because by construction that G of X plus Y, so this is equals to Gx plus Gy, and okay, so G of, so this is equals to Cgx. So automatically it is linear isomorphism, it is a linear map. So that too indicates that, so G is linear map, right? So G is a linear map, and automatically G is bijective map. So therefore, okay, so G is a linear isomorphism. A linear isomorphism. And hence, okay, so that R plus is actually isomorphic to R or R, right? So as a vector space over R. So therefore, what is the dimension of the R plus over R corresponding to this vector space structure? What is the dimension? Hello? Hello?
1.
1, right? 1. Okay. So therefore, this is 1. So that's why I am saying that. So basically, the same vector space structure you can pull back to the space capital X. Okay, and everywhere you can see. Okay, in topology, in okay, even group theory, ring theory, field theory, anywhere, if you have certain structure from one space, and if you have a bijection from a set to that space, so you can pull back the same isomorphic structure on capital X. So therefore you can make R plus is a vector space over R, and basically this is the isomorphic structure you can put in R plus, and the dimension of R plus over R is actually A1. Okay, so this is 1. Okay, so it's a very nice problem actually. And next is, and all of you know that the union of two subspaces is not in general is a subspace, right? So is there any counter example? Can you provide anyone? So, hello? The union of subspace is not in general is a subspace, right? Or vector space. Is there any idea, I mean, how to construct such an example? Okay, so so for example, if you choose that vector space V is R2, clear, and W1 is equals to the x-axis and W2, so this is equals to y-axis, clear. So W2 is equals to y-axis, and so then their union W1 union W2. Okay, so if you choose so W1 union W2. So what is this set? So this is the diagram. Okay, so the geometric figure of this set is that. So this is x-axis and this is y-axis, right? And if you take their union, so then this is nothing but is a big plus sign. Okay, and this is not a vector space, because if you choose vector 1 0 and if you choose vector 0 1, so then it will, if you add them, so you get vectors 1 plus 1 1. So this is, so 1 1 is not in W1 union W2, right? So 1 0 and 0 1, so these are belongs to W1 union W2, but 1 1 belongs to, does not belongs to W1 union W2. In fact, it is not a group actually. Okay, so therefore union of two subspaces in generally it is not a subspace. Okay, but is there any means condition? So under what condition that union of two subspaces is a subspace in a vector space? Okay, so okay, so what is the possible condition? Anyone?
W1 is a subset of W2. Yeah, W2 is a subset of W1.
Okay, so either W1 is a subset of W2 or W2 is a subset of W1, right? Okay, so okay, so okay, so just if W1, so either W1 subset of W2 or W2 subset of W1, so then W1 union W2 is a subspace. Okay, so this is a subspace. Or converse, and also the converse is also true. Okay, and also converse is also true. Is also okay. So W1 union W2 is a subspace. Is that implies either W1 subset of W2 or W2 subset of W. Okay. Well, okay. So now the one is obvious, right? So if W1 subset of W2, so then W1, okay, and or W2 subset of W1, so then the W1 union W2 is either W1 or W2, so it is a subspace. So it is very trivial. But now, how can you show that if W1 union W2 is a subspace, that implies either W1 subset of W2 or W2 subset of W1. Okay, so okay. So suppose okay that W1 union W2, so this is a subspace. Okay, so this is a subspace. So if W1 subset of W2, so then we are done, right? So if not, W1 is a not subset of W2, so then we show that okay that okay, so W2 is actually then we show that W2 is a subset of W1, right? Okay, so well, so now W1 is not subset of W2 means what? So there exists X belongs to W1 such that X does not belongs to W2. Okay, X does not belongs to W2. Clear? So if we choose that X belongs to W1, okay, such that okay X does not belongs to W2, and okay, and so now we show that the W2 is a subset of W1. Okay, so Y belongs to W2, right? So Y belongs to W2. So we show that Y is belongs to W1, right? So now that okay, so first of all, okay, so now we show that Y belongs to W1. Okay, so how can you show that? Is any idea from here? Hello, is any idea how to approach actually?
X belongs to W1 implies X belongs to W1 union W2, and Y belongs to W2 implies Y belongs to W1 union W2. Then X plus Y belongs to W1 union W2.
Okay, so X belongs to W1 and Y belongs to W2. That implies XY belongs to W1 union W2. Good. So now W1 union W2 is a subspace, right? So then X minus Y belongs to W1 union W2. Okay. So then it is either belongs to W1 or belongs to W2, right? So if X minus Y belongs to W1, so is there any problem if it is hold? So now if X minus Y belongs to W1 and okay, so suppose it is belongs to W2. So if X minus Y belongs to W2 and now Y belongs to W2, right? So that implies that X belongs to X is equals to what? X is equals to Y minus of X minus Y plus Y. So this is belongs to W2. So but X does not belong to W2. So this is a contradiction, right? So a contradiction. Okay, so this is a contradiction. And so therefore must be what? So therefore X minus Y belongs to W1. So now X minus Y belongs to W1 and X belongs to W1. So therefore Y is equals to X minus of X minus Y. So this is belongs to W1. So therefore Y belongs to W1, right? So therefore, okay, so therefore what? That W1 is a W2 is a subset of W1. Okay. And so from that you can easily says that, okay, so if W1 and W2 be to proper subspace of V, so these two is a proper subspace of V, so then okay, so V is not equals to W1 union W2, right? So if W1 and W2 is a proper subspace of V, so then V is, so then the W1 union W2 is cannot cover the whole vector space, because if V is equals to W1 intersection union W2, so then what? W1 union W2 is a subspace, is a vector space, that means it is a subspace. So therefore either W1 or subset of W2 or W2 subset of W1, right? So this implies either from the above, so either W1 subset of W2 or W2 is a subset of W1. So then what? So therefore then V equals to either W1 or W2. And this is not possible because W1 and W2 both are proper subspace, right? So this is a contradiction. Okay. So that means if you choose any vector space, so then any two proper subspaces cannot cover the whole vector space. Okay. And so next is what is the, so if we choose that three proper subspaces for a vector space V, so is there any vector space which is covered by three proper subspaces? Can you know such an, so first of all, it is possible or not? And then we will try to construct such an example. If you choose any vector space V, so it is never covered by its proper subspace, by two proper subspaces. But is there any vector space which is covered by three proper subspaces? Okay. So unfortunately, so there are some vector spaces, and okay. So for example, if you choose that, let V is equals to, okay. So Z2 square. Z2 square means is a, you know that Z2 is a field. Okay. So this, and this is a two-dimensional vector space over Z2, right? So V is equals to Z2 square, and Z2 is Z2 cross Z2. So this is a two-dimensional vector space over Z2. And okay, and if you choose that W1 is equals to 0, 0, 1, 0, and W2 is equals to 0, 0, 0, 1, and W3 is equals to 0, 0, 1, 1, right? So if you choose that three, so both are subspaces of V, and if both are proper, right? So all of our proper subspaces, and note that V is equals to what? W1 union W2 union W3 union W3. So so if V is a, so if V is that Z2 square, so then it can be possible. So it is covered by, okay, so three proper subspaces. Okay. So the covering is very interesting actually. Okay. But one can show that it is okay. So but if you choose a vector space, so note that, so this is a vector space over finite field, right? Finite field Z2. So if you choose the vector space over an infinite field, okay, so let V be a vector space, V be a vector space over an infinite field, okay, capital F. So then it cannot be covered by finitely many proper subspaces. Okay, so then, okay, V cannot be expressed as, okay, so this cannot be expressed as union of finitely many proper subspaces. Proper subspaces. Okay, it is an amazing result actually. Okay, it cannot be covered by finitely many proper subspaces. And okay, so okay, I am giving you this as an exercise. Okay, you can think about it, and okay, so if you have any doubts or any questions, So then you can mail me or you can share in a WhatsApp group. Okay, that's your solution actually. So this is very interesting. Okay, so try to think about. Okay. Okay. So okay, so how can you approach that kind of problem? Okay, so and fortunately, so first of all, I am giving is a very highly non-trivial result. So suppose let V be a vector space over field K, clear? And a linear covering of V is a collection of proper K subspaces such that V equals to union of Wi. Okay, and a linear covering is irredundant if for all J, if for all proper subset of index set, so it cannot be covered the V. So first of all, that one important thing is that linear covering always exists if and only if the dimension of V is greater than or equal to 2. So how can you show this? The linear coverings exist if and only if dimension of V greater than or equal to 2. So linear covering, what is the linear covering? The linear covering of V is a collection of proper K subspaces of such that, so V can be expressed as union of Wi. So now the linear coverings always exist if and only if dimension of V greater than or equal to 2. So how can you solve this? Is any idea? If you choose any vector space, okay. So let V be a vector space over okay over a field F with dimension of V is greater than or equal to 2. So how can you construct a linear covering? Any idea? It's a very trivial, right? Hello? So think about very natural, not is very highly okay, is very natural idea.
You could start with the basis and add one basis element at a time.
Okay. So and it's very natural because if you choose any vector, so let's suppose that alpha belongs to V, right? Is an arbitrary. So just you can V is what? So union of generated the alpha belongs to V, right? So it's very and definitely it is a covering because every the generated by alpha. Okay, so this is take from is a non-zero. Okay, so this is a definitely the generated alpha is a dimension is 1 is a proper subspace and it's a linear covering, right? Clear? Okay, so that means the linear covering is exist. Okay, if the dimension of V is greater than or equal to 2. Okay, so and basically the dimension of V greater than or equal to 2 that ensures that at least you have one non-zero element. Clear? So at least you have one non-zero element. At least you have actually two non-zero elements. Clear? So okay, so therefore the linear covering is exist, and now we define the what is the linear covering number. So the linear covering number LCV in short of LCV of a vector space V of dimension at least 2 is the least cardinality of I. That means, okay, so in the least cardinality of the index set. So of the linear covering of a linear covering that. Okay, so this is that means V. Okay, so can be covered. Okay, so is the least number of proper subspaces and then the cardinality of that least index set is basically this is a linear covering number. Clear? And now this is very surprising result actually. Is a V be a vector space over a field K with dimension of V is greater than or equal to 2. So if at least one of dimension of V and the cardinality of K is finite, so then the least covering number is cardinality of K plus 1. Okay, and if dimension of V and the cardinality of K both are infinite, So then the least covariant number is actually countably infinite. So this is the cardinality of natural number. So this is 𝕨𝕒𝕣𝕒. Clear? So that's why. So note that. Okay. So if you use that result to solve this problem, it is just follow in one line. So note that V is a vector space over an infinite field F, right? So okay. So this is a So this is the over an infinite field F. Okay, and suppose V is a V is a finite dimensional vector space. So V be a finite dimensional vector space over an infinite field F. And okay, so then V cannot be expressed as a union of finitely many proper subspaces. Okay, and note that. So this is and this is basically belongs to in A. So note that dimension of V is finite, right? So then what is the linear covariant number? Is the cardinality of K plus 1. So now in case the cardinality of K is what? K is infinite. So therefore the least covariant number, a linear covariant number is infinite. Basically infinite, right? So that means what you that means if V is a finite dimensional vector space over K, you cannot cover the vector space V by finitely many proper subspaces. So to cover this, at least you need cardinality of K plus 1 number of proper subspaces. That means infinite, right? And it is very interesting result. And so on that result, you can follow the article, the vector spaces as union of proper subspaces by Professor 𝕒𝕒𝕣𝕒𝕟𝕣. Now he is the working on as a mathematician at IISc Bangalore, and now he's won the Shanti Swarup Bhandagor Prize, and this is most scientific award in India. And also you can follow the article, the covariant number in linear algebra by Professor 𝕃𝕒𝕒𝕒𝕒. And Professor P. Okay, so there is a lots of interesting notes by Professor 𝕃𝕒𝕒𝕒𝕒 about reanalysis, is a commutative algebra, and is a linear algebra, multivariate calculus. It's amazing notes. You can see it. Okay, you can learn lot of from that. Okay, from that lecture notes of Professor 𝕃𝕒𝕒𝕒𝕒. Okay, and okay, and also you can practically you can see it that RT is a polynomials. You know that RT is a polynomial, so has a countably infinite linear covariant. Okay, in fact RT is a vector space over R, and it is an infinite dimensional vector space, right? So it is an infinite dimensional vector space, and okay, so it is an infinite dimensional vector space, and the cardinality of K is what? The same as cardinality of R. So this is also infinite. So that means it is belongs to the statement of B. So if dimension of B and dimension of K both are infinite, so then what is the linear covariant number? So this is the 𝕨𝕒𝕣𝕒. So that means that tells you that RT can be covered by countably many proper subspaces. Countably infinitely many proper subspaces. And you can easily verify it, right? Because if you choose the Wn is equals to Rnx with a subspace of polynomial of degree at most 10, right? So then what? So then the union of Rnx is nothing but is actually RT, right? Okay. So if you choose that Wn is equals to Rnx, okay. Okay, so this is Rnx, and this is the set of all polynomial. Okay, so this is the space of all polynomial, okay, of degree at most 10. Okay, of degree at most 10. And it can and clearly that Rx is union of Rnx. Okay, clear. So and each Rnx is definitely the proper subspace of Rx, And so therefore Rx can be covered by finitely many, countably infinitely many proper subspaces. Okay, so okay, so now the linear covariant number is quite interesting. You can see it if you is really interested, so you can see it. Okay, and the problem B, it is very natural problem, but you cannot use that that theorem 1 and so far. You can is a natural argument. You can see it. The vector space over an infinite field is never the union of finite number of proper subspaces. This is a very fundamental problem in the basic course of linear algebra. Okay, it's a very fundamental problem. Okay. Okay, so you anyone has any questions up to that lecture? Hello, it's fine, everyone. Hello.
Yes.
Okay.
Yes, sir.
Okay, so now we are talking about this very interesting problem. So in these problems, we will characterize all polynomials over R whose image under integer is again an integer. Okay, so if you choose a polynomial over integer, so it is automatically maps integer to integers, right? But now we will characterize all polynomials over R. Okay, so in general, a polynomial over R, it may not be maps a integer to integer. For example, if you choose that x by 2, fx equals to x by 2, this is a polynomial over R, right? And it takes 1 to half. So therefore, this is not, half is not an integer. So we'll characterize all polynomials over R whose image under integer is again an integer. Okay. So before starting this, so we'll produce is a lots of basis in Rnx. Okay, is a lots of basis in Rnx. Okay, so what is the statement of the problem 1? So let Rnx be the vector space of polynomials with real coefficients whose degree does not exceed n. Okay, and prove that if P0, P1, Pn so belongs to Rnx satisfies the degree of Pk equals to k. Degree of Pk is k for 0 less or equals to k less or equals to n. So then P0, P1 dot Pn, so that forms a basis of Rnx. Okay, so note that. So one of all of you know that. So if you choose that Rnx, so can you provide any basis in Rnx? What is the standard basis in Rnx?
Powers of x.
Huh?
The powers of x.
Yeah, good. So basically, powers of means what? So up to what?
Up to n.
Yeah. So basically 1 x squared dot x to the power n. So this is a base in Rnx, right? So this is a base in Rnx. And note that if you note that the degree of xi, so this is nothing but I, right? The degree of xi is nothing but I. So now, so our problem is very powerful. Okay, what is the statement of our problem? So if you choose P0, P1, Pn belongs to Rnx and that satisfies the degree of Pk is k, so then P0, P1, Pn is always forms a basis in Rnx. There are lots of bases you can produce and you can directly say that this is a basis. Okay, for example, so start with suppose if you choose that R3x. Okay, so then that 2x minus 1. Okay, okay, so 1 2x minus 1 x square plus 3 and okay, and x cube plus x square plus 1. So this is forms a base in R3x. Okay, okay, so from the previous days, I'll note that the degree of this is 0. The degree of 2x minus 1 is 1. The degree of x square plus 3 is 2. And the degree of x cube plus x square plus 1 is 3. So that means if you choose any set of polynomial with okay, so increasing of degree of polynomial by 1, okay, so then this set of polynomial is always forms a base in RNX. It's a very powerful tool actually. Okay. Okay, so now how can you solve this problem? Okay, how can you solve this problem? So note that you know that the dimension of RNX is n plus 1, and we have n plus 1 set of polynomials, right? So then if you see that it is a linearly independent, so then it is enough to claim that this is a base of RNX, right? So you know that the dimension of RNX is n plus 1, and if you see it, if you show that P0, P1, Pn is linearly independent, so then it is automatically follows that this is a base of RNX, right? Agree with me? Hello? Hello?
Yes, sir.
Okay. So, okay, so now we show that P0, P1, dot, Pn. So this is a linearly independent set. Independent set. Okay, so this is a linearly independent set. Okay, so this is a linearly independent set in RNX. So to show that, how can you show that this linearly independent? How can you approach it? First, we need to take what? Hello? What you need to solve a set of polynomials linearly independent?
C1 P0 plus C2 P1.
Good. So let us consider the relation that okay. So let us consider that A0 P0 plus A1 P1 plus dot AN Pn. So this will 0. And now this is 0 means this is the 0 polynomial, right? So this implies that A0 P0x plus A1 P1x plus dot plus AN Pnx. So this is 0. So this is the scalar 0 for all x belongs to R. Okay. So now how from that how can you show that these are linearly independent? Any idea? We need to show that A0, A1, AN all also are 0, right? So how can you
So
see?
maybe we can assume that one of A0 is not 0 without loss of linearity.
Okay, then
Divide it through A0 and then like change it to the other side and compare something like that.
okay, so then what? Then what your argument actually?
Like okay, so if we divide it by A0, then we take P0 x to the other side.
Okay. So then okay, so then suppose okay, suppose without loss of generality is A0 is non-zero. So then P0 is what? So minus A0 inverse A1 P1 plus dot AN Pn. So then
but P0 is of degree 1,
degree
degree
0, right?
Yeah, degree 0, and the others are of higher degree. So
Yeah. So okay, so then in the right hand side is a okay. So in right hand side, how can you know that A1, AN these are non-zero? It's maybe 0, right?
yeah,
So note that. So just is a thing is a naturally. So suppose that okay. So suppose so okay. So J is the minimum. J is the minimum among one. Okay. So we choose J Okay, so not j. So okay, so we choose suppose one coefficient is non-zero. Okay, suppose one of ai is non-zero. Okay, so then we can choose the maximum of, we can choose j is equals to what? The maximum of ai not equals to 0. So we choose maximum of index such that aj is non-zero. Okay, so this is non-zero. So that means what? So that means a0 p0 plus a1 p1 plus dot 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 aj pj, right? So aj pj. So this is 0. This is 0, right? Because aj, we choose j is maximum such that ai is non-zero. So that means aj plus 1, aj plus 2, and aj. Okay, so all of a 0. So therefore this is non-zero. Okay, so this is equals to 0. So note that, so aj is non-zero, right? So this is non-zero. So then what is the degree of the left side polynomial? What is the degree of this polynomial? Anyone?
J, right?
J, right? Good. So this is j. And this is the 0 polynomial. So what is the degree of 0 polynomial? So this is nothing, right? So then what happened? So then there is a contradiction, right? Because left hand side is a positive degree polynomial and right hand side is a 0 polynomial. It cannot happen, right? So this is a contradiction. Okay, so therefore all of ai is 0, right? So therefore that p0 p1 dot 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 pn, so all of are linearly independent. Okay, all of are linearly independent. Clear? So now using that, we will characterize that all polynomial over R, so which maps integer to integers. Okay, so we show that p maps integer to integers if and only, so there are integers n and a0 dot 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 n, px is of the form. So px is equals to summation of k equals to 0 to n ak x into x minus 1 dot 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 x minus k plus 1 by k factorial. Okay, by k factorial. Okay, okay, so okay, so first of all, first note that, so if you choose, so let pkx is equals to x into x minus 1 dot dot dot. Okay, so x into x minus 1 dot 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 x minus k plus 1 by k factorial. So first of all, the claim, my claim is, so pk always sends integer to integers. That means if you choose any integers, so that maps integer to integer. How can you show that? Anything? Anyone? If you choose a integer, okay, so then it maps also an integer. Anyone? So note that if you put an integers, if you put pkm, so then what? So this is m minus 1 dot 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 m minus k plus 1. So then this is by k factorial. So now note that in the numerator, so all integers is basically what? Is a consecutive integer, right? So this is what? So this is the product of k consecutive integers, right? Hello? Hello?
Yes, yes, sir.
And if you know that, it's a very standard fact. If you know that what? So if product of n consecutive integers is always divided by n factorial, right? Always divisible by n factorial. So that means what? The k factorial is okay, so divisible by the numerator. So therefore this is an integer. Okay. Okay, you can just using that sum of Euclidean algorithm, you can show that the product of n consecutive integers is divisible by n factorial. Okay. So then pkm is an integer. Definitely is an integer. Okay. Okay. So this is our observation. Okay. So first let px belongs to Rnx and and pz is a subset of z. So we show that px is of the form that px is of the form that summation of k equals to 0 to n ak that. And note that if these are basically x minus 1, x minus k plus 1 by k factor, this is nothing but pk. This is nothing but pk. Okay. So also note that the degree of pk. What is the degree of pk? Anyone? What is the degree of pk?
K only.
Degree of pk is k, right? Okay. So degree of pk is k. So now, okay. So now that p0, p1, dot pn. So then what? So then this forms a base from the previous problem, right? So this is a base from previous problem. Okay. And so then you can write as a linear combination of p can be write as a linear combination of p0, p1, pn, right? So then you can write it px is equals to summation of I pi x I equals to 0 to n. Okay. So note that every pi sends integer to integers, right? Okay. So this is very, very important. So now what is the remaining to show that? So the statement of B says that there are integers n and a0 dot an such that this. So now it is only remaining to show that the a0, a1 dot an. So these are integers. Then we are done, right? Okay. Clear? Hello.
Yes, sir.
Yes, sir.
Okay. Okay. So now we show that. That a0, a1 dot an are integers. Integers. And this will prove, or basically this follows from induction. Follows from induction. Induction on 0, 1 dot n. Okay. So okay. So first note that okay. First note that just a minute. Yeah. So okay. So note that P0. First note that P0 is equals to what? A0. If you put it P0, and this is nothing but actually okay. Okay. So if you put it P0, clear. So then because P1, P2, Pk all of are 0, right? If you put it 0 in Pkx where k greater than equals to 1, so all of are 0. So it is only remaining that a0 into p0x, and p0x is nothing but 1. So a0 into p0 1. So therefore a0 is an integer because p maps integer to integer. So 0 is an integer. So therefore a0 is an integer. Okay. So now we assume that Okay, A0. Okay, so now we assume that AK is integers. K is less than N. So we show that AK plus 1 integer. So then by mathematical induction, we can say all of our integers, right? Okay, so just a minute. Hello? Hello? Stop the channel for a minute. Okay, so AK is an integer, and now we show that AK plus 1 is an integer. Okay, basically we assume this, we apply the strong mathematical induction that A0, A1, dot, 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 AK, all of our integers, so we show that AK plus 1 integers. We show that is integer. Okay, and it is easily followed because okay, okay, so just a minute. Okay, so now that P, okay, so now that P, just okay, and okay, so now PM, what is PM? That PM is what? So A0. So note that. So one is important remark that PKM is also nothing but, so this is what? So this is nothing but actually MCK, right? This is nothing but MCK, right? Clear? Okay, so this is a binomial coefficient. So this is nothing but actually MCK. Okay, so so now that what is PM? So PM is nothing but actually A0. Okay, so plus A1. Okay, so MC1 plus dot dot dot. Okay, clear? Just a minute. So choose it. This is K. So choose it. This is K, and this is nothing but actually so AK. Okay, KCK. So this is K, and all of our coefficients is actually 0. Okay, you can check it. So this is nothing but AK. Just a minute. Sorry. This is, you need to put it, this is K plus 1. So then this is AK K plus 1 plus AK plus 1 K plus 1 CK plus 1. Okay, so this is K plus 1. Okay, so therefore that note that AK plus 1 is nothing but that PK plus 1 minus A0 minus A1 K plus 1 C1 minus dot 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 AK K plus 1 CK. So note that A0, A1, AK, all of our integers, K plus 1 C1, K plus 1 C2, these are all integers, and P is the integer, P maps integer to integers, so PK plus 1 is integers, so therefore AK plus 1 is integers. Okay, so therefore by mathematical induction, that A0, A1, A2, and AK, AN, so these are all our integers. Clear? So these are all are integers. Okay, so and note that the converse is automatically follows, right? So because A0, A1, AN, these are integers, and PK maps integer to integers. So then if you put any integers in P, so that maps integer to integers. Okay, so from B to A is trivial because we know that PK is maps integer to integers. So then it is obvious actually. So these are basically collection of real polynomial which maps integer to integers. So now I am asking is a one question about cardinality. So now the set of all real polynomial which maps integer to integers, So this is countable collection or not? This is countable collection or not? Hello?
Could you
Yes, sir.
repeat the question?
So now now the question is that about the cardinality. Okay, so let the script f, so is the set of all polynomial over R which are maps integer to integer. Integer to integer. So then, so script f is countable or uncountable? Okay, so then what about the cardinality of f? Any idea? So note that, so if the polynomial, if polynomial have degree n, okay, if p have degree up to n and it maps integer to integer, so then p is always is of the form in B. Px is equals to summation of k equals to 0 to n ak ak into pk. ak into x into x minus 1, x minus k plus 1 by k factorial. This. Okay. And now I am asking that, so here is no okay. So then what is the cardinality? Anything? Is it countable or uncountable?
I think it's countable.
Why it is countable?
Because we are taking like polynomials, we are taking union of polynomials up to degree n, right? Like countable union. So
Yeah. So so why that the polynomial, the set of all polynomial up to degree n, and which are maps integer to integer. So this is countable. Why it is countable? Why the set of all polynomial of degree up to n which are maps integer to integer, so is countable? The question is clear or not? Hello?
yes, this question is clear.
Yeah, so why this collection is clear, countable? So follow about the B, right? What is the structure of P?
It's like first we are taking all constant polynomials and then we are taking union like first, like in the countable union I'm saying.
So
Okay.
first of all, note that what are the coefficient of the px? So this is the rational number, right? Ak by k factorial. Ak is an integer, k factorial is an integer. So these are rational coefficient, right? Clear?
Yes, yes.
So then what? So then definitely this collection is countable, right?
Yes.
Okay. So then what? So then basically you can vary the degree. Okay, you can vary the degree of the such polynomial. So then this is nothing but the so this f, script f, is the countable union of countable set. So therefore it is countable. Okay, so therefore the cardinality of P is nothing but is a countable infinite. So this is same as the cardinality of natural number. So this is 𝕨0. Okay, so this is 𝕨0. And basically, so this question is asking in TIF, something 2021 or 22. There is a set of all polynomial which maps integer to integers. So is it is countable or not? It is countable or uncountable? Okay. Is a okay. So it's a very interesting question actually. Okay. Okay. So next we will move that the Sylvester inequality. So now what is the statement of the Sylvester inequality? That for all AB belongs to M and F, we have that rank of AB is greater than or equals to rank A plus rank B minus N. It's a very, very powerful inequality. Clear? And so now we are talking about the first problem. So let A belongs to M3C, be a matrix such that A square is equals to 0. Okay. So then, so then what is the possible rank of A? So actually show that, so the possible rank of A is either 0 or 1. Okay, so A is a matrix such that A square is 0. So then what is the possible rank of A? Okay, so okay, so problem 3. Okay, so let so we have A belongs to M3C and A square is equals to 0, right? A square is a 0 matrix. Now what is the now if you apply that on the okay, if you apply this on the Sylvester inequality, so then rank of A square is what? Sorry. Okay, so okay, so let A belongs to M3C and A square is equals to 0. So then if you apply that Sylvester inequality, rank of A square is equals to rank of A. So this is greater than or equals to what? 2 into rank of A minus 3, right? So now rank of A square is 0. So the rank of rank of 0 matrix is 0. So therefore 0 greater than or equals to 2 into rank of A minus 3. So this implies that rank of A is less than or equal to 3 by 2. So now 3 by 2 is a fraction and rank of A is always integer. So then what is the possible rank of A? Is either 0 or 1, right? Clear? Hello?
Yes, sir.
Yes, sir.
Okay, so okay, so can you know that what is the structure of the rank 1 matrix? Anyone? How particularly looks like say rank 1 matrix? Okay. Okay, well, so it's a very interesting exercise. You can solve it. Okay, so to solve that, okay, so it's required some time. So however, you can I'm giving you exercise and you can try it. And if you have any problem, so then you can mail me or WhatsApp. Okay, so let A belongs to MNF. So then and rank of A is equals to 1. Okay. So then that okay, so A is always of the form XY transpose, where XY belongs to F to the power n. Okay, F to the power n, and obviously consider F to the power n is a column vector. Okay, XY both are column vector. Okay, and so these are non-zero. So if you choose a matrix capital A is a rank 1 matrix, so it is always of the form that XY transpose. It's a very useful result. You need to solve it. Okay, and if you know that structure, you can solve this many more problem. You can easily handle it. Okay, so okay, so try to think. Okay, so any rank 1 matrix is of the form is XY transpose. Clear? And note that okay, so so now A has rank 0 or 1. So from 1, A, that A has rank 0 or 1. So now we deduce the general form of all matrices A belongs to M3C such that A square equals to 0. How the matrices looks like. Clear. And now that, so if the matrix rank is 1, so then what is the structure of that A is XY transpose, where XY belongs to CQ minus 0, right? And you know that and 0 is the rank of only what? 0 matrix, right? In 1-0 matrix, if you choose a 1-0 matrix, so rank is at least 1. So then the 0 is the only rank of 0 matrix. So then you can write it simply. So what is the answer of B? So answer of B is nothing but, so A belongs to M3C such that A square is equals to 0. So then what is the structure? So A is of the form XY transpose, where XY belongs to simply C3. Because if XY is 0, so then A is 0 matrix. And if X or Y is any one of is 0, so then A is 0 matrix. If X and Y is both are non-zero, so then the rank of A is 1. Clear? Okay. So this is the
Yes.
structure. This is the structure. Okay.
Yes, sir.
So this is the structure. Okay. And now, what is the rank of the matrix cos I minus j? Okay. What is the rank of the matrix cos I minus j? Okay. You can think about it. Just take approximately 30 seconds or 1 minute. You can think that how to compute the rank of this matrix. That ijth entry is nothing but the cos I minus j. How can you think? Well, so first note that cos of I minus j is nothing but, what is the formula? Cos I cos j plus sin I sin j, right? Clear? Okay.
Yes, sir.
Okay. So okay, that's fine. So note that, so therefore capital A matrix, you can, capital A matrix is a sum of two matrices B and C, where B is what? Cos I cos j ij, and C is what? Sin I sin j. Okay. And note that cos I cos j is nothing but, if you choose that x is equals to cos 1 dot cos n, and y is equals to sin 1 dot sin n. So then note that B is nothing but x transpose and C is nothing but y transpose. Clear? So therefore capital A is equals to what? X transpose plus y transpose. And now what is the rank of X transpose matrix? What is the rank? 1, right? Just I'm in the previous problem, what is the structure of rank 1 matrix is XY transpose. Okay, and here is Y equals to X. So the rank of X transpose is 1 and rank of Y transpose is 1. So then what is the rank of A? Is less or equals to 1 plus 1. So this is 2, right? Clear? Hello?
Yes, sir.
Yeah. So rank of A is less or equals to 2. But you can find out, you can find it. So this is exactly equals to 2. Okay. So this is your exercise. Okay. You can check it easily. Okay. Think about it. So, okay. So prove that. Rank of A is actually equals to 2. Okay. And here is obviously that n greater than equals to 2. Otherwise, it is not. Okay, n greater than equals to 2. Okay. Clear? So therefore, this is the rank of A is actually equals to 2. Okay, so now that let A belongs to MNC, be a matrix. So then A to the power n and A to the power n plus 1, that have the same rank. Clear? A to the power n and A to the power n plus 1, that have the same rank. Okay. Clear? So however, we'll move this problem after the solving problem 4. Okay, if we have time permits. Okay. Okay, if we have extra time, so then we'll move the problem 3. Okay, so this is not it's a difficult. It's a very natural approach. Okay. Okay, so before solving this problem, so before I will give you is a very important tool to compute the power of 2 cross 2 matrix using the Cayley-Hamilton theorem. This is an amazing concept. Okay, how can you compute the power of 2 cross 2 matrix using just is a very fundamental theorem using the Cayley-Hamilton theorem. So let A belongs to M2F, and we have that A square minus trace A plus data I2, this equals to 0. Okay, and you know that already what is trace and what is date for 2 cross 2 matrix. And so first problem one, okay, in problem 1 A and B, so this is just the application of the Cayley-Hamilton theorem, nothing else. Okay, so for any matrices A comma B belongs to M2R, so there is a real number alpha such that AB minus BA, that square is equals to alpha into I, for some alpha. Okay, you get some alpha such that AB minus BA, that square is equals to alpha into I. Okay. So how can you approach this problem using the Cayley-Hamilton theorem? So let A comma B belongs to MNF, and X is equals to AB minus BA. Choose X equals to AB minus BA. So this is also belongs to M2F. Okay. Okay. So so now what is the trace? What is the trace of X? Anyone?
0, sir.
Why it is 0? Why it is 0?
Trace of A, B, B are same. So
Now, first of all, you can write it. Trace of AB minus BA is equals to trace of AB minus BA. Okay, so how we so how you can write this line to this line? What is the reason?
Linear properties.
Exactly. So trace is a linear map, right? Good. So trace is a linear map, and you know that trace of AB equals to trace of BA. So then this will 0. And okay, and so let alpha is equals to date of AB minus BA, right? And now what is the if you apply the Cayley-Hamilton theorem on X, so then what is the Cayley-Hamilton theorem? And it says that X square minus trace X into X plus date X into identity. So this will 0, right? And okay, so this is date X. And now already we saw that trace X is 0. So therefore X square is equals to what? X square is equals to that minus date X into I2. So this is state alpha dash. So therefore X square is equals to minus alpha dash into I2. So this is equals to alpha into I2, where alpha is equals to minus alpha dash. Okay, and put it X. So then AB minus BA, that square. So this is equals to alpha into I2. Okay, so therefore you get a sum scalar. It's very nice. It's very trivial application of the Cayley-Hamilton theorem. Also a standard fact that trace is a linear map and trace of AB equals to trace of BA. Okay, so So then if you have any matrices AB belongs to M2R, so then there is a real number alpha such that AB minus B other square is equals to alpha into I. Okay, okay, so next is let X belongs to M2R be a matrix such that det of x square plus I is equals to 0. So then we claim that x square plus I is actually is a 0 matrix. Okay, so how can we approach it? Okay, okay. So yeah. So next. Okay, so x square plus I is actually is equals to 0. Okay. So we have that AB belongs to M2R and sorry, X belongs to M2R such that det of x square plus I is 0. Okay, so this is a 0 scalar actually. Okay. So first note that, so since X is belongs to M2R, so you can think about this is inside M2C, right? It's a complex field. Okay. Okay, so now the det of x square plus I is equals to 0. So this implies what? So det of x plus I, complex number I, identity into det of x minus II, this is 0. Okay. So then now det of x plus I, capital I, so this is a complex number, and det of x minus I, this is also complex number, and complex number is a field. The set of complex number forms a field. So then either the det of or det of, so this is 0, right? And also note that the det of x plus II, so this is nothing but actually conjugate of that. So therefore if one of is 0, so other is 0. So therefore what? So det of x plus II, so this is equals to det of x minus II, so this is equals to 0. Okay, so this is equals to 0. So now so let's suppose capital X equals to A, B, C, D. Okay, so if you put it, so then what is the x plus II? So this is nothing but A plus 1, B, C, D plus, sorry, I, D plus I. Okay, so D plus I. So now what is the det? What is the det of x plus II? So this is A plus I into D plus I minus BC. So this is nothing but AD minus BC, okay, plus I into what? A plus D. So this is equals to 0 because det of x plus II is 0. Okay. And now if you equate the real and imaginary part, you get what? You get that AD minus BC. So this is equals to 0 and okay, so okay, and just a minute. Yeah, so and well, oh, sorry, just a minute. So one terms is also there is minus I square, right? So minus I square means plus 1. So this is equals to actually minus 1. Sorry. So then AD minus BC is minus 1 and A plus D is 0. Okay. So now this is nothing but det of x is equals to minus 1 and trace of x is equals to 0. So now if we apply the Cayley-Hamilton theorem, the Cayley-Hamilton theorem says that x square minus trace x into x plus det x into I2. So this is equals to 0. So therefore what? Okay, so therefore just a minute.
Sir, the right hand side is plus 1.
Okay. Sorry. This is I square, so this is plus 1. Sorry, this is plus 1. Okay, so therefore x square plus test x is out, so x square plus I2 is equals to 0. Okay, so it's a very interesting application of the Cayley-Hamilton theorem. Okay, and the field property of complex number. Okay, and the field property of complex number. Okay, so now I will give you an algorithm. So how you compute the algorithm? Okay, how you compute the power of 2 cos 2 matrix using the Cayley-Hamilton theorem? Okay, so however, so basically, just I am telling you the algorithm, and we apply this algorithm to solve the problem is problem suppose A. Okay, and the problem B is left as an exercise, and you can try it in the in its own. Okay, so you can try yourself the problem B. So now we will solve that problem A using this algorithm. Okay, and problem B is as an exercise. Okay, so now how can you compute the power of the so matrix of product 2? Okay, so suppose A belongs to M to C is a complex matrix. Okay, and if you have a matrix over Q or over R, you can consider so directly is a matrix over M to C. Okay, so let A belongs to M to C, and let lambda1 and lambda2 be two eigenvalues of A. Okay, so then there are two cases possible. One is lambda1 equals to lambda2, another is lambda1 not equals to lambda2. Okay, so first we start with the case that lambda1 equals to lambda2. So suppose lambda1 equals to lambda2. So now we consider the matrix B is equals to A minus lambda1 into I2, because lambda, okay, so B equals to A minus lambda1 into I2. Okay, so just a minute. So note that. Okay, so if lambda1 equals to lambda2, so then what is the characteristic polynomial of A? That CAX equals to x minus lambda1, that square, right? And okay, so then by Cayley-Hamilton theorem says that CAA is equals to A minus lambda1 I, that square is equals to 0 matrix, right? Clear? Okay, so and now we choose that B is equals to, sorry. So now we choose B is equals to A minus lambda1 I. So then what? Then B square is equals to 0, right? By Cayley-Hamilton theorem. So since B square is equals to 0, so then B to the power K is 0 for all K greater than equals to 2. Okay. So now we have B is equals to A minus lambda1 I2. So then A is equals to what? B plus lambda1 into I2, right? So B plus lambda1 into I2. So then A to the power n. So A to the power n is what? B plus lambda1 I2, that whole to the power n. And now note that here we can apply the binomial theorem. Okay, so why we can apply in this situation binomial theorem? Because you know that actually binomial theorem is also hold in a ring theory, or in an arbitrary ring. Because okay, so just I am giving the statement. So let R be a commutative ring, R be a ring with unity, R be a ring with unity, and if A comma B belongs to R, oh, sorry, so this is ring R, AB equals to BA. So then A plus B whole to the power n, so this is equals to A to the power n plus NC1, A to the power n minus 1 B plus dot 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 B to the power n. So that means the binomial law is hold. Okay, so if A and B commute, so then it will work, otherwise it will not work. Okay, and if, in particular if ring is a commutative ring, so then you can always apply the binomial law for any two elements. But you know that the matrix ring is not a commutative ring, right? But in this case, B and the lambda1 I2, so these are commutes, right? So lambda1 I2 is a scalar matrix, and B commutes with lambda1 I2. So then you can apply the binomial theorem. So then this is nothing but you can And clearly that since b to the power k is 0 for k greater than equals to 2, so automatically the after n greater than equal k greater than equals to 2, all terms is vanished. So then you left only element lambda 1 to the power n I2 plus n lambda 1 to the power n minus 1 b. So you know that what is a lambda 1, and you know that easily you can compute the b. So then you can easily get the nth power of capital A. Okay, is it okay, everyone? Hello. Okay, so and now if you consider the case for lambda 1 not equals to lambda 2, so consider the matrices B is equals to A minus lambda 1 I2 and C is equals to A minus lambda 2 I2. Okay, so then what? So then by Cayley-Hamilton, then what is the characteristic polynomial? That x minus lambda 1 and x minus lambda 2 into x minus lambda 2. So then the Cayley-Hamilton theorem says that BC is equals to 0 matrix, right? Or equivalently, if you put the value C, so B into A minus lambda 2 I2 equals to 0. So now if you expand that, so then BA is equals to what? Lambda 2 into B. Okay. So now you can multiply A from the right. So then you get BA square equals to lambda 2 BA. And now BA is again lambda 2 B. So then this is lambda 2 square B. So then if you repeat that process, so you get B A to the power n is equals to lambda 2 to the power n B for all n. And now again, that okay, so that okay, so BC is equals to 0. So note that B and C commutes, right? Because these are polynomial over A. So then BC equals to 0. So then CB is equals to 0, right? So then again, BC is equals to 0. Okay. So BC is equals to CB. So this is equals to 0. And now C into B, put the value of B, A minus lambda 1 into I. So this is equals to 0. So then what? CA is equals to lambda 1 C. So again, if you, okay, so CA is equals to lambda 1 C. Again, if you repeat the process C square, right? Okay, multiply the A from the right. So this is lambda 1 CA. So this is lambda 1 square C. Okay, so therefore CA to the power n is equals to lambda 1 to the power n C. Okay, so okay, so they okay, so then what? So B A to the power n summa we have now we have B A to the power n summa lambda to the power n B and C A to the power n summa lambda 1 to the power n C. Okay, and now taking the advantages of the relation, that what is the C minus B? That C minus B is nothing but lambda 1 minus lambda 2 into I. Right? C minus B is equals to lambda 1 minus lambda 2 into I. So now start with that. So now lambda 1 minus lambda 2 into I into A to the power n. So this is nothing but C minus B into A to the power n. So this is CA to the power n minus BA to the power n. And CA to the power n is what? That lambda 1 to the power n C, and BA to the power n is lambda to the power n C. So now you can easily compute B and C. Just B is nothing but A minus lambda 1 I2 and C is equals to A minus lambda 2 I2. Okay, so therefore A to the power n is what? 1 by lambda 1 minus lambda 2, lambda 1 to the power n C minus lambda to the power n C in B. So you know what is C, what is B. You can just in one line you can compute the C and B. So then this is the A to the power n in the case of the distinct eigenvalues. Here, and it is very smoothly you can compute it. So there is no lots of calculation anything. Okay. Okay. So okay. So okay. So using this algorithm, you can. Okay. So now this is our last problem, that we solve that just only problem 2A. So A is equals to 2 by 3, 1 by 3, 1 by 3, 2 by 3, and B equals to that. And basically these problems is I'm taken from the ISI PhD entrance, and I think it is okay, asking in 2007, 17 or 18, anything. Okay, 17 I think. Okay, so okay, so note that the V1 is V and Vn plus 1 is equals to A Vn. Okay, so here Okay, so here Vn plus 1, so this is equals to A Vn, and V1 is equals to V vector, and this is AB. Okay, and now so this is what? So this is A. If you put that Vn, so this is A square Vn minus 1. Okay, and if you dot dot dot, okay, put it, so this is nothing but A to the power n P1. Okay, so this is equals to A to the power n into AB. So then first of all, what is the question? Question is that we need to find out the limit n tends to infinity Vn. So before this, we need to find out what is Vn. So note that, so Vn plus 1 is A to the power n into AB, right? So now if you compute that nth power and you multiply AB, the vector AB, so then you get Vn plus 1, and then takes the limit. Okay, then takes the limit. So now we have that A matrix is what? A matrix is, okay, that 2 by 3, 1 by 3, 1 by 3, 2 by 3. Okay, so 2 by 3, 1 by 3, 1 by 3, 2 by 3. Okay, so okay, so this is nothing but actually 1 by 3 into 2, 1, 1, 2. Okay, okay, so everyone, okay, so okay, so now okay, everyone try to find out eigenvalues. Okay, so what are the eigenvalues? So take 1 and 2 minutes and then compute it and tell me what is the eigenvalues of A. Okay, so okay, so what is the lambda 1 and what is the lambda 2? Find out it. What is the eigenvalue lambda 1 and lambda 2?
1 and 3, sir.
1 and 3, right? Okay, is it okay? The answer of lambda 1, lambda 2 is same as every other everyone. Okay, okay, so clearly these are distinct, right? So these are distinct.
Sorry,
And,
sir. Lambda 1 equal to 1 by 3. Lambda 2 equal to 1.
so this is 1 by 3 and this is 1.
1, yes, sir.
Okay, is it same for everyone?
Yes, sir.
Okay, so this is 1 by 3 and lambda 2 is equals to 1. That's fine. Okay, so okay, and also I'm telling you that okay, so you don't need to in mind that formula of A to the power n. Okay, so it is because in exam, so you can, if you mistake some minus and anything, so you basically the answer you will get the wrong. So basically totally follows compute. Okay, so totally the computational power, it just follow the algorithm. Okay, so just start with B and C and try to same approach. Okay, so if you you can remember that, okay, you can okay, in mind that formula, but I'm telling you that it's not need not to the okay, so follow this formula. You can easily find out the formula. Okay, so to throughout this, okay, so to solving this problem. Okay, so okay, so however in the, okay, so now just so first we find out that B and C. Okay, so what is B and C here? B is equals to A minus lambda 1I and C is equals to A minus lambda 2I. So what is A minus lambda 1I? And so this is 2 by 3 minus 1 by 3. Okay, 1 by 3 and 1 by 3. So 2 by 3 minus 1 by 3, right? Now what is C? So this is 2 by 3 minus 1, 1 by 3, 1 by 3, 2 by 3 minus 1. Okay, so Yeah. So this is equals to, okay, 1 by 3, 1 by 3, this, and C is equals to, okay, minus 1 by 3, 1 by 3, 1 by 3, minus 1 by 3. Okay. So, okay, so, okay, so now we, here we apply directly, but when you solve the problem or compute any the power of matrix, okay, in the exam, so you can through the algorithm, not not try to putting it as a formula, but you can, okay, you can be wrong actually. Okay, so if there is some plus minus is, okay, is problem, so then you can get the wrong answer. Okay, so then here is a to the power n is 1 by lambda 1 minus lambda 2. Okay, so first of all, okay, so then here is a to the power n is what? 1 by lambda 1 minus lambda 2, and this is lambda 1 to the power nc minus lambda 2 to the power nb. Lambda 1 to the power nc minus lambda 2 to the power nb. Okay, so now what is the lambda 1 minus lambda 2? Lambda 1 minus lambda 2 is 1 by 3 minus 1. So this is minus 2 by 3, right? So that means you get minus 3 by 2. And here that lambda 1 to the power n is nothing but 1 by 3 whole to the power n, okay, into c. And note that from c again you get 1 by 3, and this is minus 1, 1, 1, minus 1, and plus and minus, and you get b. So this is lambda 2 is 1, so this is you get 1 by 3 into 1, 1, 1, 1. Okay, so so this is minus 3 by 2, and what is the what is this? So this is 1 by 3 to the power n plus 1. So you get minus 1 by 3 to the power n plus 1, minus 1 by 3, right? And okay, 1 by 3 to the power n plus 1, minus 1 by 3, and okay, 1 by 3 to the power n plus 1, minus 1 by 3, and this is minus 1 by 3 to the power n plus 1, minus 1 by 3. Clear? And okay, so now if you take the limit as n tends to infinity, right? So therefore limit n tends to infinity, n is what? So this is minus 3 by 2. So this is minus 1 by 3, minus 1 by 3, minus 1 by 3, minus 1 by 3. Right? Clear? And this is you get half into 1, 1, 1, 1. Is it okay? Sorry. So this is a to the power n. Limit n tends to infinity, a to the power n. Okay? Hello? Hello?
Yes, sir.
Okay. So now what is Vn plus 1? So this is equals to what? A to the power n into V1. So this is equals to half into 1, 1, 1, 1. Sorry, it take the limit. So limit n tends to infinity, Vn plus 1. So this is equals to limit n tends to infinity, a to the power n, okay, into V1. So this is equals to half into 1, 1, 1, 1 into AB. So this is what? So this is A plus B by 2, A plus B by 2. Right? Clear? Okay?
Yes, sir.
Okay, and try to solve the problem B. So first find out the a to the power n, and then you need to find out for which a that limit n tends to infinity, a to the power n is convergent and is different from 0. Right? Clear? Okay? And the problem 3, you can think about it, that why the rank of a to the power n and a to the power n plus 1 is same. Okay, so and try to write the solution and then put in the WhatsApp group. Okay, so and if you have then, and if you not done so, then I will help you definitely. Okay, so this is the so now if you have any questions, so then you can ask me. Okay, so
Okay, thank you, Samit, Ghosh, for this nice session. We shed light to some ideas like linear coverings of vector spaces that can be taken as a project topic for MSc or BSc students.
yeah, so this is very good, good project topic, because you need not any higher tool actually. Okay, so then any graduation BSc student you can take as a project actually. It's very nice.
And also will be really useful if they are doing some internship or get some chances like that to be associated with a linear algebra professor. Then it will be very nice if we have some extra reading from outside the syllabus. So I'm encouraging the degree students and PG students to proceed more on this particular topic that Samit has shared with us. Okay, once again, I would like to thank Samit and dear participants. Now it is your time to share your feedback or raise any question if you have. Yes.
Okay, and also I am telling you that the computation of matrix power is also very useful when you try to solve some the Diophantine equation, in particular the Peel's equation. Okay, and the Peel's equation and the reconciliation. So this will very help you that the computation of matrix power. And for that, I will recommend that you can follow is a very nice book, that Essential Linear Algebra by Professor Tirur Andescu. Okay, so in these books you can find out that the some application of the matrix power, computation of matrix power, and this is basically is very nice approach to solve the reconciliation and so some Diophantine equation. It's very important tool, and also it is very important in the case of in particular in data science field. Okay, so lots of algorithm is related to the computation of matrix power. Okay.
Yeah. Okay. Samit.
Yeah.
Yeah, Samit, it will be better if you can share the PDF of today's class, and also I think you have promised that to share answer to some problem that we didn't discuss in the class.
Yeah. Okay, so I will share I will share that PDF.
It will be better to include some reference books, the names of some reference books in that. Then it will be really useful for the participants.
Yeah, so for problem books, I will recommend that one is very nice problem book. Is all of you know that it's very standard. So this is the Problems on Linear Algebra by P.R. Holmes. Okay, it's a very nice book. And as a textbook, I will recommend that the 𝕄𝕒𝕒𝕚 feedback. So these are very classical book, but so in competitive exam, so those books are important, which are classical as well as, so there are lots of information is there. Because in competitive exam you need to take care. Okay, so lots of information, right? So because in limited time you need to solve some problem, and you need to also mind in some trick. So that's why I am telling you that I am particularly I am realized that it's very useful for competitive exam. So follow the linear algebra book, Essential Linear Algebra book by Professor Tirur Andescu. I will send you the PDF. Okay, and also you can see that the feedback book, but 𝕄𝕒𝕒𝕚 and anything book. So these are basically take little more time. Okay, you need to understand. But so the Tirur Andescu book is very friendly. You can in short time you can get is more information. But after that, you can you need to study 𝕠𝕤𝕐𝕐 because there are lots of important techniques is there. Okay, but I am telling you that corresponding to 𝕠𝕤𝕐𝕐, you need to follow that T2 books is very useful. And not only that, when you study that geometry and topology, so there is a lots of information is there. And also there are some important, for example, bilinear form, inner product, and quadratic form. So these are also important. All of you know that, right? Okay.
Okay, Rajvel, you can speak now.
Sir, which book? I want to the reference book only, sir. You also say that, no, sir. That is my question, sir.
Yeah, so basically I am telling you that initially you follow that the books of books by T2 So because this is very friendly book and you can read quickly and you can learn lot of in a short time. Okay, and because these books is basically is built on the approach of the Olympiad. Clear. So this is basically the very problem solving. These books is very written by problem solving approach. So that's why it would be very useful for everyone. And also definitely the 𝕠𝕐𝕐𝕐 book is very important. But I am telling you initially you need to follow that kind of books for competitive exam. So these are basically the problem solving approach.
Yeah, Samit, it will be better if you can include the names in that. See, sometimes the participants may not be able to follow the names from your pronunciation. So it will be better in that references that we can share it as a PDF along with the recording of the program. Okay.
Okay, so I will share a PDF. Also, okay. So just a minute.
Yeah, we can share it along with the recording. Okay.
Okay,
so Rajvel, could you introduce yourself? And for all the participants, if you share a feedback, it will be better if you can keep your video on and introduce yourself. It will be very nice to see you all in our platform.
Yeah, so I'm okay. So written the author name in the okay. So Essential Linear Algebra by Professor T2 Okay.
Okay, thank you, Rajvel. Yeah, yes, Rajvel, you can.
Good afternoon, sir. I am Rajvel from IISER Tirunelveli.
Okay.
Doing M.Sc, sir.
Yeah.
Actually, very thankful for your wonderful lecture, sir. I really understand everything, and because of the 𝕃𝕒𝕒𝕚𝕚 theorem, I can do many things. And now only I can understand that, sir. Really, very thank you, sir.
Thank you. Okay. So okay. So and anyone and also I am telling that if anyone have any questions or any doubts, so you can easily contact with me and don't hesitate. So okay. So I am trying to help as much as possible. Okay.
Thank you, Rajvel. So you have got a friend in IISER Kolkata now. So see, this type of connections will be really useful in your studies. Rajvel is in IISER Trivandrum.
Yeah. So
see, our platform that
so that kind of platform is particularly is important because for connection, right? So for communication, this is very important.
So dear participants, feel free to share your feedback with your video and introducing yourself. Yes. Yes,
Hi, sir. I'm Shyama Kumar. I'm BSc final year at Aspirants University, Bangalore. So today's class was really nice. I was able to learn many new concepts. Thank you so much, sir.
Okay, thank you.
Thank you, Shyama. Yes, Dharmendra.
Good afternoon, sir. I am Dharmendra Singh from Kasganj, UP, near Aligarh and Agra. This class was very nice, and last problem was very nice. And you told some Olympiad related book also. I want to ask you told about some I forget, sir. Some application of linear algebra in Diophantine equation.
Yeah.
Kindly, can you tell some little more about linear algebra connection with Diophantine equation?
Yeah, so linear algebra is very closely related to Diophantine equation, because all of you know that, first of all, if you solve the finite set of equation of linear equation, so then definitely basically you can solve using the linear algebraic tool. And okay, so and another is, if you solve the particularly one time, all of you know that what that x square minus dy square, right? So this is a kind of type of that Peel's equation, and you can solve this equation using the matrix power. Okay, and this is totally linear algebraic tool, and it's many more because linear algebra is one of the central topic in every branch of mathematics and every field of every field of science, actually, because physics, chemistry, everywhere this is basically okay, so lie in the center. And also computer science, because okay, eigenvalue, eigenvector, so these are practically that connected to that okay, so Google page rank and anything, right? So okay, so these are very practically this is linear algebra is very, very important, and theoretically is definitely, because when you study differential geometry, when you study topology, manifold, everywhere, because there is a the base is a lots of lots of concepts is there, and totally all concepts in differential geometry, manifolds is totally built on the linear algebra, right? So if you know, if you have enough knowledge on that field, so you can easily understand is any other branch of mathematics. Okay, so
Yes, sir. Thank you, sir. Thank you sir. Thank you very much.
Okay, thank you, Dharmendra. Yes, others?
Good afternoon, sir. I
Yes.
am Shikha, and I'm from Jharkhand. I've completed my integrated M.Sc in mathematics and computing. Right now, I'm preparing for CSIR NET. Sir, your session was really wonderful results, and the proof that you have given, it was it became easy to understand the results, and it was really a wonderful class, sir. And it was more research oriented type session. I liked it a lot. A unique and different kind of session it was. And so my question is this: like, if one one have to choose some their research topic, then what are points that person should keep on mind, and what are topics, what are points the one have to consider while choosing a research topic? And in case if one wants to choose a topic in real and in linear algebra, the most practical application related research topic, then what one should choose?
Yeah, so basically, if you choose that some research area related to linear algebra and the practical application of linear algebra, you can choose your field as a data science or computer science, clear. So you can see, or cryptography, you can see there is a lots of real practical application of linear algebra. And okay, so and also first of all, you need to think that what field you like, actually. Okay, so if you like that algebra, okay, so then you need to find out which institute is better for you. Okay, so not only that, suppose you like that analysis and you apply some other institute where is basically lots of faculties on algebra, right? So then definitely that institute is not good for you. So, and suppose, and if you like algebra related field, so you need to apply some institute, and you need to focus which institute where the algebra, okay, there is a lots of faculty on algebra field. Okay, so that is also keep in mind. And okay, so and for PhD interview and any kind, basically, okay, so you need to at least 2 topic is important for PhD interview. So if you choose that algebra analysis, or you can choose the algebra topology, or you can choose analysis topology. Okay, because because interviewer is not always asking from one field. Okay, so they are asking for questions from many fields, because in 20 to 30 minutes, okay, so they are judged from various field. Okay, so from asking that questions. Okay, so from also, if you think that from that you need to prepare for interview for at least 2 topics is very well. Okay, and I am also telling that, okay, so you need to study that not as exam purpose. Clear? So because okay, so suppose you clear that all competitive exams and many more, because okay, and also you okay, so should clear the comprehensive exam in PhD, or as well as the coursework, right? And in coursework, so if you have enough knowledge, so then you can better feelings, okay, or you can feel is a or you can enjoy. Okay, so if you have is a lots of gap of knowledge, so then you can depressed, right? Okay, so I am telling that everyone that okay, so learning and gain knowledge and try to solve problem, not particular only solve problems. Okay, so then you can okay, you can easily realize that definitely you have some okay, grow on the knowledge of mathematics. Okay, so and this is particularly important, because the competitive exam is okay, so and so for preparing of competitive exam, so you need also that also you need to mind that the gaining knowledge of mathematics, right? So this will important, because and you can realize that when you go some prestigious institution, and all of you already prepare for research, and if you have some gap on the knowledge, you can really depressed on that situation. Okay, so that's it.
Yeah, the competitive examinations will open a path to move, but for moving in that path, certainly you need the concepts. A sound knowledge of the idea is very much essential.
Yeah, so
Thank you, sir.
Okay, thank you, Shikha. Any others?
Hello,
Yes.
sir.
Yes.
I'm Soumya Babu, final year PhD student from Kerala. Thank you for your class. It was you were presenting each concept clearly. It was like we can understand each concept thoroughly. And thank you for sharing some resourceful books with us. Thank you so much for your time.
Thank you, Soumya. Others?
Hello, sir. I am Praveen KC from Kerala. Your class was very easy to follow. I am a second year student, but yet I could follow it properly. So thank you for the great session. Thank you.
Okay, thank you.
Thank you, Praveen. Any?
Good afternoon, sir. Sir, I'm a second year BSc student from Kerala. I found the class really interesting. I was able to learn a lot of new concepts. The class was really nice. Thank you for the class, sir. Thank you, Vinod, sir, for organizing this class. Thank you.
Okay, thank you.
Thank you, Gopika. If any of you would like to share a feedback, please make it now. Yeah, Lakshmi.
Hello, sir. I am Lakshmi. I am from TMC College, Tirur, Kerala. Thank you, sir, for this wonderful class. It was really interesting and informative, and you explained each and every concept very clearly. And thank you, sir, for spending your valuable time with us. And thank you, Vinod, sir, for conducting this class. Thank you.
Okay, thank you.
Lakshmi. If anyone else? Yeah, Vandana.
Hi, sir. Good afternoon. My name is Vandana and I'm from Kerala. I'm in my final year BSc degree. Thank you so much, sir, for this session. We are so grateful for this, for the knowledge you shared with us, and I'm sure this will be a great help for each one of us. Thank you for the effort and time you put into teaching us. Thank you.
Okay, thank you.
Thank you, Vandana. So I think.
Okay, so thank you for everyone for valuable feedback. Okay, so I'm really enjoying that. Okay.
Okay. So thank you, Samit, and be with us in future also. I request you to engage few more sessions in our platform according to the availability of your time during your research schedule. Once again, thank you everyone, and wish you all the very best. Thank you.